Okay, we're continuing to look at some integrals, and now let me talk about another method of integration. Let me do a couple of examples, then we'll go back to our review problems. What if I was going to try and integrate something like this? Now, you know, in the previous video, if I can find the problem, oh yeah, here it is. We had this one where I wasn't able to integrate it as it is, but I said, you know what? I can go ahead and multiply out this 2x plus 1 squared, and I did some algebra and finished it. So theoretically, I could do that here, x cubed plus 1 to the 5th, but you know what I have to do? I'd have to multiply this parentheses by itself 5 times. That could get awful messy. I think I would end up having a exponent of x to the 15th. Who knows, it may take me 20 minutes just to do it. It's going to be a big mess. But there's another method that we can try. It doesn't always work. But for us, it's going to work a lot, especially in the problems they give us, because they sort of make the problems such that they work. Integration by substitution. So let me briefly explain the concept, work a couple of examples, then we'll go back to our review assignment and see how it applies. The idea here is, as it sits now, I don't know how to integrate this, and it's too painful to try and multiply it out. Here's the principle of integration by substitution. You notice here, I've got a bunch of x's, and I'm taking the integral with respect to x. So x is every place. Integration by substitution says you have x's. What we're going to do is we're going to introduce this new variable u, and if we do it in a smart way, eventually all the x's, even this dx here, all the x's in the integral will turn into u's. And when we do that, we're going to do it such that when they turn into u's, then we can actually integrate it. So when we switch it to u's, we're switching it with a purpose so that when the variables become all u's, we can actually perform that integral. So once we integrate it, then we have the integral in u's. And the last step is then you switch the u's back to x's, and then you've actually solved the integral. So the trick here is, it's not really a trick, is the key is when we first define this u, we have to know what to choose inside the integral. Now in a case like this, sometimes this is more of an art than a science, but if you do them a while, you get a knack for it. If you have stuff inside of parentheses raised to a power, almost always, whatever's inside the parentheses, we're going to define as u. So you notice there's no exponent here. I'm just taking whatever is inside the parentheses, and I'm going to call that u. And then here's something interesting. Here's how I like to do these, which I think makes it pretty simple. Once I define my u, I'm now going to take the derivative of u with respect to x. So now it just becomes a derivative problem. Well, it's a derivative of x cubed. Bring the 3 down. You subtract 1. Derivative of 1 is a constant, it's 0. This is the u dx. And what I always do now, so this is the same step you do every time. You define your u, then you take the u dx, and then, so I'll say, let's do steps. Define the u, find du dx, And then the third step, solve for the dx. In other words, get the dx by itself. So if I multiply both sides by dx, but if I want to get dx by itself, if I want to solve for dx, I'm going to divide both sides by 3x squared. I end up with this. I mean, it looks sort of ugly. In fact, I've got two variables here. I've got an x squared here and a u here. Once I've done this, I'm now going to substitute into my original integral. I'll rewrite it here. And if this works, when I'm all done substituting, there will be no more x's and only u's. And beyond that, when I turn it into u's, it's actually something I can integrate. So the key is, let's start with the u part. We call this u. So this x squared tags along for now. X cubed plus 1 is what I called u. The dx up here, I figured out what dx is equal to. Now initially, this doesn't look too great because I have the variable u and the variable x. I've got them both together, which we can't really work with that in math. But if you look a little closer, you notice this is x squared. This is x squared in the denominator. You know what happens? Those cancel out. And when you do that, I have the 1/3 still. 1/3 u to the 5th du. So I've achieved my first goal of taking this integral. Instead of x's, I want only u's. And the key is, now I can actually integrate this expression. Right? You add 1 to the exponent. And you put that at the bottom. Now if I simplify this, this 6 is going to go in the top actually. So now I've done some work, but you notice now I still have a u here. If my problem began with x's, obviously when I take the integral I want the answer to be in x's. Right now I've got u's here. So now to switch back to x's, whatever I define my u to be, I just now plug this in for u, x to the 3rd plus 1. So 2u to the 6th becomes and now we're done. So this is called integration by substitution, and it's the same routine every time. Let me do one more example. This one may not be obvious, but when you start to see these, then hopefully you'll start to work with them. 1 over x plus 1, integral with respect to x. It doesn't look very complicated, but we don't actually have a way to integrate this. However, I can do substitution here. Let me go and do it, and then you'll see it. I'm actually going to let u equal the denominator. So once again, then I take du dx. Du dx is just 1. If I solve for dx, basically dx equals du. So now let's go back here and get rid of all the x's and replace them with u's. 1 over x plus 1. X plus 1, I'm now calling u. Dx actually equals du. So I've went from an integral I don't really know how to integrate to u's, and it's 1 over u. I know how to integrate this one. Matter of fact, that's natural log absolute value of u. So now I've integrated. The last step is now replace the x with the original definition. And now we've integrated it. All right, so now we're going to pick up with, I believe, number 9. And now I think most of these we're going to solve, have to use integration by substitution. So let's see how this works. Now we haven't done an example yet with the exponential function, but just so you know, if you have an exponential function, the u almost always equals the exponent. So anytime you define your u right away, you go ahead and take the u dx, derivative of this, derivative of 5x is 5, derivative of 3 is 0. Now solve this thing for dx. Once you get dx by itself, you get 1/5 du. Once you've done that, now you go back to your integral and try and see if you can replace the x's with u's. E to the 5x plus 3, 5x plus 3 we're calling u. So e to the u dx is 1/5 du. So if I sort of, maybe I'll bring the 1/5 all the way out, because hopefully you see we actually can integrate this e to the u with respect to u just e to the u. Last step, replace the u with x. And there we go. All right, let's do the rest of these. Hopefully as we do these, you'll start to get a knack for it and be able to do them yourself. Number 10, 1 over 3x plus 5 dx. Let's do substitution. Let u equal 3x plus 5. Now we take the u dx, it's just 3, and solve this thing for dx. 1/3 du. Let's go back, try and get rid of these x's and see what we have once the dust settles. 3x plus 5 is u, so 1 over u. dx is 1/3 du. If I bring the 1/3 out front, this looks familiar. When I integrate this, this is actually the natural log function. So 1/3 natural log absolute value of u plus c. Now that I've integrated it, I replace the u with my x. There you go. I guess I should be checking these answers as I go. All right, let's just keep rolling along. Once again, hope you see the pattern. You do the same kind of thing over and over again. So 11, 2x e to the x squared minus 1, integrated with respect to x. That's getting a little more complicated. You got a 2 and an x and then an e to this. I'm just telling you, almost always when you have the exponential function, the exponent is almost always what you need to set u equal to. Then du dx, 2x, solve for dx, 1 over 2x du. Now let's replace everything we can over here with x's and see if we can get some u's to show up. Now you notice this x here, I've got nothing to replace it with, so I just have to bite the bullet. I'm trying to get rid of x's, but for now, nothing I can do. Let's see if something good happens. However, e to the x squared minus 1, x squared minus 1 is u, so e to the u, and then dx is 1 over 2x du. So initially, this looks sort of messy because I have x's and u's together, which I don't want. But here's what happens with substitution. If it works correctly, you notice I got an x here and an x in the denominator. They cancel out. So I got 2 times 1/2. Those actually cancel out. By the time the dust settles, I've got e to the u du, so the x's do actually disappear. And I know how to integrate this. You just rewrite the exponential function. Last step, get rid of the u by plugging in our x equation. Don't need that there. And now we've integrated this. All right, 2 more of these. Actually, if I check that one, number 11, no, that looks correct. Number 12 is 3x. You know, it says square root. I'm going to go ahead and change it just to save time, because that's what I always do when we do math with radicals. We almost always change them to rational exponents. Looks a little messy. Once again, whenever you have parentheses, almost always you set the u to whatever's inside the parentheses. Now be careful. This exponent right here, this 1/2, is not included in u. U is just always what's inside the parentheses. So now du dx, solve for dx. Now let's substitute in to our integral and see if something good happens. Ideally, the x's all disappeared. I'm left with u's, which I can integrate. 3x, move the 3 out. X, I'm sort of stuck with for now. X squared plus 8 is u. Dx is 1 over 2x du. And now I notice x here and x here, so that's good news. Those cancel. And I'm left with the integral 3/2 times the integral of u to the 1/2 du. I can use the power rule for this. So you add 1 to the 3/2, and this exponent goes on the bottom. I simplify these cancel out actually. So I have u to the 3/2 plus c. Now if I bring back my x's, x squared plus 8 raised to the 3/2 power plus c. All right, now there's one more that I think we have to use substitution on. Two x to the 4th over x to the 5th plus 1. Integral with respect to x. It's getting a little more complicated. Once again, when you got something like this, You can think of this as in parentheses. I'm going to try and start there. You always take du dx. Integral this is 5x to the 4th plus 0. Solve for dx. Well, let's substitute and see if anything good happens. 2x to the 4th, I'll bring the 2 out here. X to the 4th, I'm sort of stuck with it for now. X to the 5th plus 1 is just u. Dx is 1 over 5 x to the 4th du. You notice the x to the 4th is cancel out. By the time the dust settles once again, we actually know how to integrate this. This is going to be the natural log. Last step, switch back to x's. And that should be the answer. All right, one more topic to cover. Everything we've done so far, these are called indefinite integrals. When you do an indefinite integral, you always have to, this is called the integration constant. The plus c is always on the end. But the last part of this review, we're going to look at some definite integrals, and you will not find it that hard. So let me do that on the next video, and then we'll be finished.